Here is a tiny atomic nucleus. How can these nuclei provide enough energy to supply electrical power to cities as large as Toronto or Montreal? In 1939, scientists discovered that a large nucleus, such as uranium-235, would become unstable when struck by a neutron. This could cause it to split into two nuclei of about the same size and release 2 or 3 neutrons. Nuclear fission was the name eventually given to this process. If we place the reactants on one side of a balance and the products on the other, we will find that the products are always lighter. Clearly, a mass has disappeared in the nuclear reaction. What happens when a mass like this is lost? Einstein's mass-energy equation predicted that a large amount of energy should be released when the mass is converted to kinetic energy of the fission products. The fission of a uranium nucleus releases more neutrons. These, in turn, can collide with other uranium nuclei. A chain reaction then becomes a definite possibility. What we need now is a contraption that takes advantage of these chain reactions. A contraption which uses fissionable material as fuel and harnesses energy released during nuclear fission for practical, everyday applications. Today, we have those contraptions, nuclear reactors of several designs, which harness nuclear fission throughout the world. Most reactors use uranium-235 as a fuel. It has 92 protons and 143 neutrons. Less than 1% of natural uranium is U-235. More than 99% is uranium-238. Among so many U-238 nuclei, what happens when a lonely U-235 nucleus undergoes fission? A chain reaction is unlikely because many of the neutrons released are gobbled up by the U-238 nuclei to form U-239, an extremely radioactive isotope of uranium. Other neutrons simply escape from the sample because they are traveling too fast to fission another nucleus. Only a slow-moving neutron stands a fairly good chance of initiating fission in a uranium-235 nucleus. A fast neutron speed cannot be reduced through collisions with other uranium nuclei. But if a relatively small mass like a water molecule is present, the water molecule can absorb a large amount of energy from the neutron. The process slows down the neutron. A number of these collisions will reduce a neutron's speed until fission is likely to occur. The name moderator is given to a material used to slow down the neutrons. Ordinary water is a good moderator, but it sometimes absorbs neutrons and so removes them from the reaction. Heavy water is a very effective moderator. It contains an isotope of hydrogen called deuterium, which has a proton and a neutron. It slows down the neutrons, but rarely absorbs them. But with slow neutrons, a nuclear reaction can get too much of a good thing. Too many slow neutrons means too many fissions, and too much energy released as heat. A chain reaction that is uncontrolled could produce so much heat that a reactor could literally melt down. A safety feature is necessary. Within the core of the reactor, surrounded by the uranium fuel, control rods can be lowered and raised. Cadmium is the usual material for these control rods because When it is inserted between the uranium atoms, cadmium slurps up neutrons. This slows down the fission reaction. Let's examine how all of these ideas can be put together to design a reactor which will produce electricity. The fission reaction takes place inside a containment building. Its walls help shield the environment from radiation produced in the core. In this simplified reactor, uranium serves as the fuel. Water functions as a moderator, which slows down the neutrons. The water also serves as a coolant, carrying heat out of the reactor core. To start the fission reaction, the control rods are raised. Now, the fission reaction is not initiated by U-235 colliding with a slow neutron, but by a uranium-235 nucleus undergoing a rare spontaneous fission. The neutrons which are released are slowed down by the moderator, which surrounds the fuel rods. If at least one neutron from each fission causes another fission, a chain reaction is produced, which can be adjusted or stopped completely using the control rods. The kinetic energy of the fission products causes the temperature of the fuel to increase, which in turn increases the temperature of the moderator, which surrounds them. Even when it reaches extremely high temperatures, the moderator does not boil. Boiling doesn't occur because the reaction takes place in some form of reactor vessel, which is very highly pressurized. As a result, the water becomes superheated. This water is pumped to a heat exchanger. In the heat exchanger, the heat is transferred to the water in a separate container to produce steam. This steam drives a turbine, which then turns a generator to produce electricity. Transmission lines conduct the electricity to waiting consumers. Not all of the energy produced by a nuclear reaction goes to the consumer, however. A significant amount is carried away as waste heat in further cooling processes. This heat may be pumped into a large body of water. In other reactors, it is discharged into the atmosphere through a cooling tower. The majority of the commercial reactors used around the world are more complex than the simplified model we have examined. However, the basic process going on inside them all is the same. Nuclear power now accounts for a respectable percentage of electrical energy produced in the world. But the changes occurring in the fuel itself have presented us with a bag of mixed blessings and challenges, which we will examine in our next program.